right, guys, last day of notes for organic chemistry. So we're talking about organic reactions. So for the regions, you're going to have to identify reactions, identify types of reactions, predict products, that kind of stuff. Some more in detail than others. So what's really important to notice about them in general is that these are very slow reactions. Years and years ago in the lab, I made soap with Mrs. Mitchell, and the actual making of soap, which we're going to talk about a little bit, is pretty easy. You just put lard or fat with sodium hydroxide, and then you mixed it up, but then you had to wait. You had to wait about 2 weeks for it to completely form soap. It's extremely slow. A lot of students are used to that instantaneous reaction and it's done. These are very slow. And this is because they are covalently bonded. Remember the sharing of electrons. And so since we're breaking those strong bonds and then making new bonds, and there's a lot of interactive and overlapping valence orbitals, and so it takes a while. So here are our organic reactions. Our first kind is combustion, which we've talked about before. Combustion is burning of organic compounds. So we have a hydrocarbon, which now we know what a hydrocarbon is. Remember, some amount of carbons, some amount of hydrogens. This is always going to be O2. Why is it O2? Diatomic oxygen. Always going to produce water and carbon dioxide. This is what we call complete combustion. We're forming carbon dioxide. However, if you don't have enough oxygen when you're burning this, so, let's say you're running your car in a closed garage, that's not good. You don't have enough oxygen. So instead of carbon dioxide being produced, you would form carbon monoxide, and that's called incomplete combustion. So that's why you definitely should not warm up your car in the garage with the door being closed, because carbon monoxide is extremely toxic and dangerous. So what would be the complete combustion of propane? Now we know what propane is. Meth, eth, prop. That means C3. Well, how do I figure out how many H's there are? 2 ways. One, you could draw it. 1, 2, 3. Fill in all the H's. 1, 2, 3, 4, 5, 6, 7, 8. The other way you could do it would be using reference table Q, the homologous series. I know that it's alkane, so that's going to be CnH2n plus 2. So if N is 3, what is H? 2 times 3, which is 6, plus 2 is 8. So there's 2 ways to figure out propane. Drawing it is always good practice. So for combustion, we have to combine with oxygen, and then you're always going to produce the same 2 things, carbon dioxide and water. Wait, is this a reaction? That means we always have to balance it using coefficients. Oh, man. Well, let's do it. Good practice. Tally up your atoms. Sorry, it's messy. 1, 2, 3. Okay, do your O's last. All right, let me change color here. Let's put a 3 here. It's going to be good to our C's. What's that also going to change? O's. So 6 and 1 is 7. Okay, what about H's? Looks like I've got 8 over here. How am I going to get 8 hydrogens? You in the back. Oh, yeah, of course. Nobody's there. So we have 8 here. What does that also change? 4 plus 6 is 10. Now, how do I get 10 oxygens? Put a 5 here. Whoops. Darn it. There we go. All right, good review. Combustion. This is a complete combustion because it forms CO2. The next is called a substitution reaction. So if you think about it, when I am absent from class, a substitute comes in for me. If I am absent from class, they're not going to hire 5 substitutes for me. They're going to hire 1 substitute for me. One goes out, the other goes in. Now, let's say there were 2 teachers teaching the class, and they're both going to be absent that day. Well, then 2 subs would be needed. A substitution is when we take 1 or more hydrogens out and we put something else in. There are a few other details here. Saturated hydrocarbons. Saturated, substitution, what kind of bonds? Single bonds. So all of these S's should help you remember. A substitution only happens with single bonds. Okay? So if we have ethane and chlorine, let's draw it. Meth, eth, all single bonds. And for the sake of example, I'm going to draw my H's in. This does not look pretty, but you get the idea. And chlorine. What does chlorine look like? And as I'm looking in my notes, I noticed that I did not put in valence electrons, and I absolutely should. Why is it Cl2? Diatomic. Hofbrinkel. Okay, so I kind of like to think of this as like the game. This is the bench. So if we're going to sub out one of the H's with one of the Cl's, here's the game. So one of the H's is going to come out of this, and one of the Cl's is going to come in here. Doesn't matter where you put your Cl. And here's the bench. This is 2 valence electrons. I don't know if that made it better. So with a substitution, 1 goes out, 1 goes in. You can have 2 come out and 2 come in also. That can also happen if you want. So there's that one. Then I can do, I shouldn't have erased all of it. Whoops. Okay, so there's that and there's that. I wish I could go fast. Oh my goodness. Fast mode. H, 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 H. See why we don't draw them? Because it takes so long. So this time, let's take 2 H's out and put 2 Cl's in. And it doesn't matter where you put your Cl's. H, 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 H. Let's put this Cl here. You know these are H's even though I didn't write them. So if 2 Cl's went in, 2 H's come out. Diatomic. So either of those examples, the one I just erased and then this one, these would both be considered a substitution with single bonds, which are saturated hydrocarbons. Now, what if you just want to bring them all together? Add them together. The only way you can add stuff, find additional spaces, is to break a double or triple bond, because that's the only way you can make room. You can't make carbon have more than 4 bonds. The only way you can do it is if it wasn't bonding to 4 different things to begin with, and then we just break them. So what do I mean? Let's do it. First of all, you absolutely need an unsaturated. So that means double bond alkene, triple bond alkyne. So here's my ethene, double bond. Why are these H's at those weird angles? Well, it's because the double bond makes it a linear, rigid structure. And let's choose chlorine again, which I noticed in the notes. Once again, I forgot my valence electrons. Make sure you include them. Okay. Now, this is called addition, which means we don't want to take anybody out. We want to include everyone. And the only way we can find spots for these 2 is to break that double bond. So we still have our 2 C's. This C on the left had 2 H's. This C on the right had 2 H's. But now we've got spots on either side to add the Cl's. Now you don't have to put the Cl's at this 3 o'clock and the 9 o'clock spot. You could put them on any place you want. But notice we have 1 product being formed. 1 product. You are adding them together. It's called an addition reaction. And it can only happen when you've got a double or triple bond, an unsaturated compound. Esterification. Gee, what do you think we're going to be making here? How about an ester? How do you form an ester? You don't remember old Granny Esther? She lived a really hard life. How did she get so old? Well, she took acid and she drank alcohol. She made some poor choices. So also, old people usually have a glass of water nearby. So esterification, acid and alcohol producing your ester and water. I have never seen you be asked to draw esterification on the regions. It's mostly, what is this reaction? Recognize it. Recognize the ester. But we're going to draw it here because why not? Ethanoic acid and ethanol. So let's start with ethanoic acid. How many carbons? Meth, eth. Oic acid. If you forgot what acid's functional group looks like, take a look on table R, and then of course fill in the rest of your bonds. Uh-oh, I made too many bonds to carbon. Did you see my mistake? This carbon has 1, 2, 3, 4, 5 bonds now. Get rid of that. You should only have 4 bonds to carbon all the time. So there's ethanoic acid. And then let's draw ethanol. 2 carbons. Now watch what I'm going to do here. There's really no wrong place to put the OH, but watch why I put it here. Also, why did I draw it backwards? So that I didn't have 2 bonds to hydrogen. Can't do that. The reason I drew it this way is to show you why the reaction happens. I would take the OH from this and an H from this. What is that? What did I form? H2O. Now, what would happen if now that I took that out, I slide the rest together? If I slide the rest, what do I want? Indecision. If I slide the other 2 together, watch what I get. C double bonded O. Here's my H's. Single bond, 2 and O, 2A, 2 carbons, do. I see her. I see her smiling at you, offering you some pineapple candy. Old Granny Esther. There's the ester. Functional group, C double bonded O to a single bonded O. There it is. So, like I said, on the regions, it's mostly going to be, what kind of reaction is this? And you recognize that it's an ester because you know what an ester looks like. I was talking about this earlier. Saponification. Who's ever played jumble, word jumble? I used to love it. See this right here? If you jumbled those words, those letters, what would you get? Saponification is the formation of soap. All you need to do is recognize what a saponification reaction is. You don't need to write it or draw it. You just need to know that to form a soap, esters, fats, inorganic base, something like NaOH, and you're going to form alcohol and soap. Soap is what we call a salt of a fatty acid. Too much bio for me. We're moving on. Fermentation. So you bought some apple cider when you went to pick apples, and you put it in the back of your fridge, and you forgot about it. You forgot about it, and you forgot about it. And all of a sudden, you're like, oh, I really go for some cider. Pull it out, and whoa, it doesn't smell the same. Don't you dare taste it. It has fermented. It is no longer cider. It's more like apple cider vinegar at this point. So fermentation is formation of alcohols. So you've got to have sugars. Sugars and the introduction of yeast. Yeasts are actual living beings. And so what the yeast does is it chews up the sugar and creates alcohol and burps out carbon dioxide. So that's why beer and that kind of stuff, it has bubbles. Now, wine would be bubbly, but they remove that carbon dioxide. Polymerization. Polymerization is when you make long chains. Poly meaning many, mer meaning little piece. So you put all these many little pieces together and you form large molecules. So we use polymers in like practically everything. There are natural ones and there are artificial ones. So polyester, does that sound like it exists in nature? No. So this is synthetic. Notice I don't say man-made because women can do anything. Nylon, Teflon, plastics, okay? So this happens in nature. I don't want to go through all those. Natural, things like starches, cellulose found in plants, proteins, and silk from silkworms and spiders. Synthetic, things like nylon, polyester, silicone, Teflon, nylon, that kind of stuff. I've got nylon twice. Polyester, synthetic. How would you recognize a polymer? I'm going to give you two ways. I don't think I've seen these. Oh, thanks, Screencastify. I haven't seen these things in a while, like on the Regents, but you will need to recognize them. So when you add them together, it shows N. What does N mean? N means a huge number. That's a number sign. So this means you just have multiple joined together. And another way that you can have them come together would be condensation. You know condensation? That's giving off liquid, gas to liquid. This is just water is being given off. And there's a lovely diagram in your notes, which you cannot see here because of Screencastify. I don't know how deep they're going to go into this on the Regents, but you got that. Petroleum. So petroleum, I don't know that it's on the Regents necessarily anymore, but I'm just gonna go with it. So petroleum, this is stuff we dig up from the ground, and we're digging up that it's not quite gasoline at this point. This is like the oils, and we need to purify it. We purify it through a process called fractional distillation, which is when we boil it off in different fractions. So at certain temperatures, we just pull off what we've got, we use it. The distillate, that condensed vapor, is collected in several fractions, like I was saying. So here's our picture. We start, and again, it's really kind of hard to read, but we'll try our best. So crude oil comes from the ground, petroleum, like way down in the ground, like, deep water horizon kind of stuff. And then we boil it. We heat it. The first ones to boil off are very small carbon chains, 1 carbon to 4. We use that for liquefied petroleum gas, like your propane tank, that kind of stuff. Then we keep heating it, and then we pull off 5 to 9 carbons for chemicals. We keep heating it, 5 to 10 gasoline. Petrol. This be like a British diagram here. Gasoline for your car. Keep heating it. Jet fuel, paraffin. Keep heating it. Diesel. Keep heating it. Lubricating oils and waxes. Keep heating it. Fuels for ships. Keep heating it. Like blacktop for the roads. So thick. If you look, small molecules at the top, super low boiling point, so they're going to come right off. Very, very volatile, means they're going to turn to gas right away. Very easily flows easily, and ignites easily. As you heat it, it becomes thicker. High boiling point, not going to go to the gas, very thick and viscous, will not ignite. Think about, if you've got one of those little lighters, butane lighters, I don't know why you would, but you can shake it around. You can hear that liquid inside. And then down here, you think of those people who are paving the roads, and they're scraping and pushing that black tarry stuff. Very different. It comes from the same source, but it's been refined into this thick black stuff. Last thing is called cracking, and this is definitely honors only. So college prep folks, you can tune out or listen just to learn. There's value in that. So cracking, this is when you have really long particles, long molecules. So let's say we've got like, the blacktop kind of stuff. We don't want blacktop. I don't want that. I need to fill my gas tank. So I'm going to take that blacktop stuff, break it down, and that will thus increase the supply. 2 ways to crack: thermal, meaning with heat; catalytic, meaning with a catalyst. So that's kind of cool. Not in the Regents, Good to know. Because you know what? We don't always want stuff to, fuel a jet. I want to fuel my car and go to Target and find something fun. So we will use these processes. We are done, folks. Thanks for watching.